Let's apply this to a situation where we have a 5 centimeter domino supporting a ramp 60 centimeters from the point where the ramps intersect, and a 5 centimeter die supporting this ramp at the 40 centimeter position. Okay, the slope 1 is going to equal 5 centimeters over 60 centimeters, which equals 0.083. And we're not looking for a whole lot of precision here, so I'll even ignore that 3. That slope is about 0.08. And over here, the slope 2 equals 5 centimeters over 40 centimeters, approximately equals 0.13. Okay, so our P1 and P2 vectors will have an angle here theta 1 plus theta 2 is going to be approximately 0.08 plus 0.13. That'll be in radians, which is 0.21 radians. Now, if you think back to some of the approximations we made on, or some of the calculations we made on previous discussion, just a couple of clips earlier, this isn't a hugely small angle. It's you know, if you use this angle, you got about a 2% error in the approximation that the hypotenuse equals the run and the things that result from that. But what we're really trying to do here is trying to figure out if the momentum change here due to the collision of part of the P1 momentum with this ramp is going to make a significant difference in the momentum that we get going up the ramp. In other words, do we lose an appreciable amount of momentum, or if we wish, an appreciable amount of energy, which is related to but not equal to the change in momentum. So we got an angle of 0.21 radians. This implies that P1 perpendicular is 1 minute. I'll be done with this in just a second. Okay, that P1 perpendicular is, and that's a magnitude of P1 perpendicular, is approximately 0.21 times P1. Okay, so we get this result, and of course you need to fill in some of the blanks here, but this is the result that we ultimately get for the perpendicular component of P1. Okay, so we've concluded that the magnitude of P1 perpendicular is about 0.21 times the magnitude of P1, where this could be off by as much as a couple percent. That probably wouldn't even be a 0.01 though. Might be plus or minus 0.01. And you can again work that out and see just how close it is. So it follows then that what's the magnitude of P1 parallel? Here's P1 parallel. This is P1, P2, P1 parallel is this vector, P1 perpendicular is this vector. Well, P1 parallel squared plus P1 perpendicular squared equals magnitude of P1 squared, okay? So it follows that, first of all, P1 parallel is P1 minus P1 perpendicular. Take P1, subtract P1 perpendicular, you have a vector here, gives you this vector, okay? You should be familiar with how that works. And the magnitude of this vector then is just by the Pythagorean theorem, P1 squared minus P1 perpendicular squared. P1 perpendicular being 0.21 P1, we can factor out of P1, we get 1 minus 0.21 squared, which is about 1 minus 0.04. Square root of that is square root of 0.96 is about 0.98. You get this. You should think through how we get from here to here using the approximations we've been talking about. But the conclusion is that the momentum that we have going up the second incline should be 98% of the momentum we had coming into the second incline. The magnitude of the momentum we have when we go up the second incline should be about 98% of our original momentum, meaning that momentum changes, even on fairly big slopes like 0.13 and 0.08, there isn't a whole lot of momentum loss. Now, kinetic energy loss is going to be proportional to the square of momentum loss for reasons that you should become very familiar with as we work through the chapter on momentum. But it turns out that the anomalous results that we have from the experiment aren't explained by the momentum loss, provided this entire analysis is correct.